Now we come to the concept of torque. Okay, what is torque? We have seen what force is. What is force? Something that accelerates a mass, correct? Now what is that which rotates something, which rotates a rigid body which has its axis fixed? Later we'll extend it to when the axis is not fixed. The concept remains the same, but currently we are trying to understand a rigid body which has a fixed axis. Then what is it that rotates it, or what are the factors which are responsible for the rotation of an object? We understand. Now let us try to see. This is a door, right? And it is hinged here. Okay, so that is the fixed axis of the door. This is the axis of the door. Okay, now what does rotate this door? What rotates this door? Is it force? Force. So fine, you say that force rotates it, and perhaps so try to and perhaps you're right, but maybe in a limited way you are right. Okay, so let us try to think. I apply a force on this door here. You see, I apply a force here. So obviously the door rotates. I apply a force here, it rotates. Now I apply the force here, the same force. It requires more force for me to rotate it in the same way as I was able to rotate by putting my finger here. We get that? It is no wonder that these doorknobs, they are the farthest. As I start going nearer to the axis, it starts becoming more difficult for me to rotate it in the same manner as it was earlier rotating. Correct? Now let us try to think. You said force is required. Now I kind of hang on it. Is it rotating? No. So somehow the direction in which I apply the force, that is also important. Do we get that? The direction is important, correct? The force is important, and the distance from the fixed axis is also important. Do we see that? Yes, so here only, if I keep it here only, I apply a small force, it goes like that. I apply a large force, it goes like that. So force is important, the direction of the force is important, and what is important is how far away have I applied it from the fixed axis. So in comparison with the force that we have been seeing, the torque, the thing that rotates it, and we name it differently and we call it torque, moment of force, that is not so simple. Why? Because it starts depending on so many other factors. We understand? It starts depending on so many other factors, at least three, right? Apart from force, the distance at which you apply the force, the direction in which you apply the force. See, the same thing, a very small force was able to rotate it, but when I absolutely hung onto it, right, my whole weight, almost all of the weight, almost 80% of the weight is getting applied and still is not moving. Correct. So the direction of the force is equally important. It is not merely force that rotates something. Correct? Fine. Though it looks complicated, but we will be able to find out a relation between this, and we should be able to develop an objective formula for what we call the the moment of force, that is torque, that is what rotates a body. Do we get that? And that is what we will be doing exactly, right? So we just now saw that something that rotates, okay, that the cause of rotation, the cause of translation was what? Force, is it not? Cause of translation is force. So what is that? We are onto a question where we want to ask what is that which causes rotation. Okay, so cause of rotation is what we call moment of force, and that is what is called a torque. That is what is called a torque. Do we get it? We right now saw that torque is not as simple as force, right? So it depends on at least 3 factors, correct? It depends on at least 3 factors. So moment of force, it depends on what? Number 1, we saw that it does depend on force, but not only on force. There are many other factors. Even if we increase force, in one of the situations where I just hung onto the door, it was not rotating, it refused to rotate. Correct. So it is not only the force, it is also the direction of the force. Direction of the force. And what is that? Another thing, its distance from the fixed axis. Correct? So distance from the fixed axis. Correct? So distance from the fixed axis is something that is very, very important. Is it not? All of them are important, right? So distance, direction, and the force, the magnitude of the force itself. Correct? Now let us explore. So what I am trying to say, there are 3 things. Now whenever I try to find out its relation with one of them, I have to keep everything else the constant, same. Okay? Everything else the same. So maybe you saw the door like that, isn't it? There were some patterns like this on the door, though that is not very important, but to give you an idea what we were doing, say something like this, okay, and yes, something like this, okay. This is how it was, and it was right. So you remember it? Okay, so it was something like this, and this is the fixed part, right? So this is my fixed axis. Now what happens? So it's free to, and this was the doorknob, right? I'm not such a bad artist after all. No? Fine. So so I was, what did I say? So the torque, everything else remaining the same, that torque we denote it by tau. Okay, after all, what happened? Everything else remaining the same, say when I was pushing it here, so I do not change the direction, I do not change the distance. You understand? And if when I was pulling it very slowly, or compare that to when I was pushing it with some greater force, what had happened? It moved faster. So somehow the tendency of rotation went up with the magnitude of the force. We get the point? So the torque tau is directly proportional to force, while these two remained the same. Right? That's how you establish a relationship between 2 or 3 or 4 variables, right? So when you are deciding about one, you keep everything else the same. That's how the experiments are also conducted. What happens? You want to see whether this leads to better growth of children. So you take a group of children. What do? They should be having the same weight. Their age should be the same. Okay. Maybe the genetics should be the same. No? Genetics, because maybe genetically some are far superior, so even with the same amount of food they'll grow faster. It happens, right? So if everything is the same and you vary one thing, so you want to understand whether say something, say vitamin D leads to better growth or better absorption of calcium or better bone density. So what do? You take them the same, you give them the same food, same environment, same output, that means same game, same kind of activities, and you vary one. So maybe this group you supply with something and this group you do not. So what happens? Then you'll be able to see that if 90% of this group may be gained in height or compared to them, then it will be considered that it is this variable that led to this. Correct? So whenever you're doing that, even in everyday life, correct? Even in everyday life, and we seldom understand these things. So we'll pop a pill just saying that, okay, so you had fever, yes, and you got it with the shiver, yes, and you sweat while the fever went away, yes, and what was the medicine? This, and you also pop one. There are so many other variables that you have not looked at. Maybe vomiting tendency, maybe whatever. You understand? So that's what I'm doing. So when I say the magnitude of the force, I keep everything else the same. Then only you'll understand. So it is directly proportional to force. The same torque tau, what happens? How is it proportional to the direction? Everything else remaining the same, direction. So the point remains the same, the force remains the same, and I vary the direction. So I see that when it acts perpendicular to it, correct, it was the maximum, and when I was pulling kind of parallel to it, parallel to the door, to the plane of the door, I was hanging here, no? So kind of this, I was hanging, right? Like that. The other hand is there. I was hanging like that. Okay? So it didn't move. And here it moved. So here, even with my finger push, it was moving. So somehow, what is happening? When I am applying the force like this, when I am applying a force like this, my torque is 0. And when I am applying it like this, it is a maximum. Now what does that mean? if I say the point where I apply the force, okay, so maybe this point, the point where I apply the force, if I connect it from here, from the axis here, okay, and I say this is the force that I am applying, okay, so this is the force that I am applying. This is the force I am applying. Then what happens? Somehow, if this is my R, okay, this, let me draw it in red. If my R is this, if my R is this, if my R is this, the red one, okay, and my F is this.
So in this case, you have taken R as the shortest distance from the axis.
Yes.
Okay.
Yes. So, this is the shortest distance, yes. So what happens when they are aligned? They are in the same direction. That means the angle between them is 0. Then my torque is 0. So what I am saying? How do I define that angle? I define this angle like this. I am drawing it here separately, right? So this and this. So when I applied it, so this is R, this is F. So when the angle is 0, if theta is equal to 0, and how do I define the angle? After making them co-initial. Never forget it. That is a convention. So if theta is equal to 0, torque is 0. If theta is equal to 90 degrees, torque is equal to maximum. And here it is minimum. Now, what is that which is a minima? Is there a function which is a minima at theta equal to 0 and a maxima at theta equal to pi by 2? What is that function? Sine theta. The function sine theta, if you look at it, it is like this. This is pi. This is pi by 2. This is 0. This is not, and this is 1. So it takes a maximum at theta equal to pi upon 2. We get that point. So somehow it seems to be directly proportional to sine theta. You get the logic? Also, distance from the fixed axis, when I was pushing it from here, I found it more difficult to push it with the same force. No? If you become closer, maybe even your whole weight will not be able to rotate it. So somehow it is also directly proportional to R. Is it not? So it means that tau is directly proportional to R and F and into sine theta. And this goes away. So the proportionality goes away. I am left with a constant of proportionality. What happens now? Do you remember your Newton's law? There F was directly proportional to that and there was a KMA, and since I am defining it for the first time, I have that whole freedom of doing what? I say fine. If this is 1, this is 1, this is 1, I define the torque to be 1. Why do I do that? I say fine, if 1 Newton is acting at a distance of 1 meter at an angle which makes an angle of 90 degree with it, I define it as 1 unit of torque. I am free to do that.
Why? How?
It's not about how. We had seen F became kma. I said fine, I'll define the force that accelerates 1 kg of mass by 1 meter per second square, that I define as 1 Newton. What happens? 1 becomes k into 1 into 1, so k becomes 1. Or 1 is equal to k, so k is equal to 1. I do not want to drag this constant of proportionality with me. Why should I? You understand the concept? Why should I? For example, after all you will be defining, you say no, that I'll call as 2 units of torque. Fine, then you drag a 2 with you. So you always keep on writing torque is equal to 2rf sine theta. Then someone will ask you, from where did this drop and why? Then you will say, this is how I had defined it. Then if you have got that discretion of defining, why did you define it like that in the first place? Why are you carrying a constant unnecessarily? Unnecessarily. Understand the logic. We do not want to carry a constant unnecessarily. When I have the discretion to define it, why will I define it as 2? You just tell me, someone comes in and says, why not half? Why not half? Then you will be carrying a half. Then why not 1/10? So we say, why do we carry it at all? So why not make it 1? Understand the logic. It's convention. Okay. After all, in this case, see, try to understand with this. You have a 1 kg mass. You apply some force and you see that, okay, it's accelerating by 1 meter per second square. Maybe you calculate it by finding out the velocity after 5 seconds. Say the velocity becomes 5 meter per second. Fine. So you say, whatever is this force, whoever this force is, I'll call this 1 Newton. You get the point? You get it? How discretionary it is in the beginning. 1 Newton is not an absolute thing. Okay, it's not absolute. Okay, it's your discretion. Okay, so the same kind of discretion I'm applying here. So this makes k as 1. You understand? So k is equal to 1. So tau is equal to r f sine theta. R f sine theta. Okay. Now torque has to be given a direction. What is the reason? Because torque is something that should be producing an acceleration on the same lines as force produced an acceleration. Correct? Here it should be producing an angular acceleration. So I write this torque produces an angular acceleration, alpha, which is a, and why should it produce an angular acceleration? Because this is the rotational equivalent of the force. I'm trying to develop that, parallels. I'm trying to develop parallels. So which is a vector? So alpha is a vector. Obviously a scalar cannot cause a vector to get produced, right? You cannot bring a scalar vector with a scalar, though you can produce a scalar with a vector, dot product. Correct? So torque has to be a scalar. Correct? So this torque produces an angular acceleration alpha, which is a vector. Hence, this torque must have a direction, must be a vector, and hence must have a direction. It must have a direction. Do we get that? No? So it must be a vector and must have a direction. Now what direction? What direction? So let us come to this. It starts rotating. Suppose it starts rotating like this. Then what kind of torque will you apply? Obviously like this. Okay. So maybe something that rotates it like this. No. So if it is, say, stationed here, I'll kind of try to push it like this. Or here, look at this door. So I'm pushing it like this. So it starts rotating this way. Okay. So what is the direction of the angular velocity? What is the direction of the angular velocity? Upward. What is the direction of angular acceleration? Upwards. What should be the direction of the torque? Upwards. I cannot be applying torque in this direction and producing an acceleration in that direction. Correct? Why? Because I was not able to apply a force in this direction and an acceleration in that direction. Force and acceleration were in the same direction. Correct? You understand? It makes sense. So the very reason for which you defined omega upwards and which looks awkward. No? The whole thing is rotating like that and omega is pointing up. And upwards nothing is happening apart from stars being there. Correct? So again it will look weird but sensible to define the torque in the upward direction. Do you get that? In the upward direction. Now what happens? So torque has to be like that. Okay? In this case. Now try to think. RF sine theta is the magnitude of the torque. Does it remind? And R is a vector. Now so many things come in one after another. R is a vector. No? Position vector. F is a vector. Two vectors should be giving you a vector. So tau is a vector. Somehow they get multiplied and have a factor of sine theta. Now that is more than a hint. No? It's not a hint, it's the answer itself. So it tells you tau is equal to, obviously there will be cross product of R and F. The only trouble, why? Because R and F, it involves sine theta. Okay? It involves sine theta. The only trouble is R cross F or F cross R. Oh, how did you know? R cross F. See, look at this. This is my R, right? For the perpendicular force, I am free to move it perpendicular to the door, right? If that is the force I have applied here. If I have applied a force F here, I have moved it parallel and made it this, correct? Now R cross F has to be up. So this is my R, this is the red pen is R, the red vector is R, the blue pen is F, this is F. What direction I move it so that it gives me a vector upwards? This on this right hand screw rule, a bottle like that, if you rotate it opens up, linear motion is upward, so it has to be R cross F. F cross R will go down. So that is.
Why can't we take it down? What's the problem with taking it down?
Same reason. You cannot apply a torque downward and it produces an acceleration upward.
Oh yeah, yes.
Right.
Yeah.
So I am taking my torque up. So I take my torque here only. So the blue pen, the torque up.
Clockwise jack to down.
Huh? Yeah, obviously. Clockwise from above. There's a bottle with someone?
F plus.
This bottle, see, if I am taking it counterclockwise, it's coming up, so it opened. Clockwise, it's going down. Linear, the linear motion. It's going down. R cross F is down. F cross R, sorry. That goes down. I don't want that, so it has to be R cross F. Okay? So what started by rotating a door ended in this. And you should be pretty clear why. Each and every step of it. Why not this? It actually fell into place. Understand? So that is how I define my torque. Correct? Fine.